Hey everybody, it's Ripley. Welcome back. It's me. We're going to talk a little bit about section 9.6, vectors in space. I pilfered a couple of good pictures off of the internet to show you how vector in space works. Now, I want to show you a couple things first. First and foremost is the orientation of the axes. Typically, you can choose them however you'd like. I kind of like this one because the x and the y axis, excuse me, are in the same spot. And the z sort of comes jutting out at you. It's hard to write or to make a three-dimensional object in two-dimensional space. So that works best with the way that my brain works. This guy is a little trickier because notice the x is out here, the y is out here, and the z comes straight up. Either way, again, they're kind of arbitrary. Now, I want to show you something here. Hopefully you remember this from Algebra 2. In 3 space, instead of ordered pairs, which we use in 2 space, there are ordered triplets. So if you look at this and you orient yourself by your axes, again, you just want to orient yourself that way first. Notice x is 5, so this point could be written as 5, y is 8, and then z is 3, right? So that would be the ordered triplet that defines that point. And hopefully you remember that from Algebra 2. That was kind of a fun exercise. Well, think about it. It's a vector. So if it starts at the origin, if the initial side is at the origin and the terminal side is at a point, then we know that we could write this vector if we had to as in that vector notation, which could be 5, 8, and 3. Now, remember in 2 space, we said that vectors could be written as AI plus BJ. Well, in 3 space, we just add a k to this thing. So we can write it as AI plus BJ plus, whoops, CK. Sorry, you guys, I'm getting pinched over here. All right, so I could write this vector up here as V equals 5I plus 8J plus 3K if I wanted to. All right? Now, once you've got your brain wrapped around how vectors in space work, all of the rules that apply to vectors in 2 space, when I say vectors in space, I really mean 3 space. We can sort of stick that in parenthetically. All of the rules are exactly the same. Nothing has changed. So, for example, if I think about it, if I want to write the vector that goes from point 1 to point 2, remember how we had this kind of crazy notation that looked like that? And let's say that point 1 is equal to, could be written as x1, whoops, x1, y1, z1, and then I need to throw some commas in there, don't I? And point 2 is equal to x2, y2, z2, throw my commas in there again. Then I can rewrite this vector if I wanted to as x2 minus x1 I plus y2 minus y1. Whoops, that should be a plus, huh? Looks like a minus. J plus z2 minus z1 k. So if you notice, nothing has really changed. I remember how we did that in 2 space. We just didn't have, we just didn't have these terms involved. These guys right here weren't part of the equation. All right, so that's a vector in 3 space. Oh, incidentally, think about it. We'll play with this a little bit in class if you have questions about it. In 2-dimensional space, we know that the distance between any 2 points is x2 minus x1 squared plus y2 minus y. Boy, it doesn't want to write pluses today, does it? y2 minus y1 squared. Now think about it, in 3 space, because really it's just a double application of Pythagorean's theorem, and I can show you, if you can't wrap your brain around that, I can show you in class. This could be written as plus z2 minus z1 squared. It's exactly the same. All right, just kind of have that, you have your brain wrapped around that. I think we discussed that back in Algebra 2, so that shouldn't be anything earth-shattering. All right, so let's talk about what we're going to do with these bad boys, okay? First and foremost, if I've got a vector defined this way, and I know that distance is defined this way, then what's the magnitude of a vector? Well, the magnitude of a vector is just the length of the vector. It's the distance from one point to the next, right? And if I write my vector like this, where it's, remember, vectors are movable. I can move them wherever I want, where its tail is at the origin, and its head, as it were, is at the terminal point, remember initial and terminal, nothing has changed again, then this is simply the square root of a squared plus b squared. Boy, it does not want to write pluses today, does it? Plus c squared. That's all that it is. All right? Now, let's say that I want to dot v with w. All right? And I've got v over here. Let's let v equal a1i plus b1j plus c1k. And let's let w equal a2i plus b2j. My pad hates me today. Plus c2k. Well, what do you think that the dot product is? Remember, the dot product's just a quantity. It doesn't have any units associated with it. It's just a1, a2 plus, ooh, it wrote plus right, b1, b2. Notice how I blame my technology. A good carpenter. I know, leave me alone. All right, easy peasy. That's how you dot vectors. Nothing to it. Okay, how do I add vectors? So if I go v plus w, I'm not going to bore you with too much of this. Let's go plus and minus. I'll kill two birds with one stone. I know how you guys love it when I do a whole bunch of different examples. All right, so v plus w is just a1 plus and minus a2 times I plus, whoops, plus, there it goes again, plus b1 plus and minus b2j, and then plus c1 plus minus c2. Okay. Now, if you think about it, any vector can be written as a vector in 3 space. Right? Really, any vector can be written as a vector in n space. It's just that these coefficients, let's say that I've got v equals 3i plus 4j. We know what that guy looks like, right? It looks, I go over 3 and I go up 4 and it looks like that. Well, and this is at 3, 4, right? Well, that's in, this is the x, this is the x, and this is the y, right? There's no z, so I could simply write that as plus 0k. Nothing to it. Again, don't want to bore you, don't want to get crazy. Now, what if I take a scalar? I'm going to write this as s. I know it's a lousy, I don't like writing s's mathematically because they look, especially that one, it looks just like a 5. If I go s times v, that's just a scalar, right? So this is just going to be s a1 I plus s b1 as opposed to a2 b1j plus s c1. Okay. All right, nothing to it. Again, don't want to get crazy. All that we're doing is extrapolating what we know about 2-dimensional vectors to 3 space. Same thing. If I want a unit vector in the same direction as the original vector, I simply take the vector itself and I divide it by its magnitude. And that scales it down to a unit vector. Think about this. What this really is we're multiplying, think of this as 1 over the magnitude of v, remember magnitude is just a number, times the vector itself. This guy right here is just a scalar. It just shrinks it down by 1 over its magnitude, which is helpful. And then the exact same move that we used, remember back when we were first playing with these guys? This is u times the magnitude of v is equal to v. All right? Same rules. Again,